In this chapter, you'll learn how Windows uses TCP/IP protocols and standards to create and manage network connections, including how computers are identified and addressed on a network. You'll also learn to connect a computer to a network and how to set up and secure a small wired or wireless network. This chapter prepares you to assume total responsibility for supporting both wired and wireless networks in a small home office (SOHO) environment. In Chapter 16, you learn more about the hardware used in networking, including network devices, connectors, and cabling, networking tools, and the types of networks used for Internet connections. In Chapter 17, you learn how to support applications using a network and how to troubleshoot networking problems. So let's get started by looking at how TCP/IP works in the world of Windows networking. Understanding TCP/IP and Windows networking. When two computers communicate using a local network or the Internet, communication happens at three levels: hardware, operating system, and application. The FireSD step in. Communication is one computer must find the other computer. The second step is both computers must agree on the methods and rules for communication, called protocols. Then one computer takes on the role of making requests from the other computer. A computer making a request from another is called the client and the one answering the request is called the server. Most communication between computers on a network or the Internet uses this client-server model. For example, in Figure 15.1, someone uses a web browser to request a web page from a web server. To handle this request, the client computer must FireSD find the web server, the protocols for communication are established, and then the request is made and answered. Hardware, the OS, and the applications on both computers are all involved in this process. Let's FireSD look at the layers of communication that involve hardware, the OS, and applications and then see how computers are addressed and found on a network or the Internet. Then we'll see how a client-server request is made by the client and answered by the server. Layers of network communication. When your computer at home is connected to your Internet Service Provider, ISP, off somewhere in the distance, your computer and a computer on the Internet must be able to communicate. When two devices communicate, they must use the same protocols so that the communication makes sense. For almost all networks today, including the Internet, the group or suite of protocols used is called TCP/IP, Transmission Control Protocol, Internet Protocol. Before data is transmitted on a network, it is FireSD broken up into segments. Each data segment is put into a packet. The packet contains the data, called the payload, and information at the beginning of the packet, called the IP header, that identifies the type of data, where it came from, and where it's going. If the data to be sent is large, it is FireSD divided into several packets, each small enough to travel on the network. Part of the information included in a packet header is the address information needed to find the computer that is to receive the packet. The address information includes three levels: the address at the hardware level, called a MAC address, the address at the OS level, called an IP address, and the address at the application level, called a port address. Communication between two computers happens in layers. You can see how communication starts with an application browser, passing a request to the OS, which passes the request to the network card and then on to the network. When the request reaches the network card on the server, the network card passes it on to the OS and then the OS passes it on to the application, the web server. Listed next is a description of each level of communication. Level 1, Hardware level. At the root level of communication is hardware. The hardware or physical connection might be wireless or might use network cables, phone lines, for DSL or dial-up, or TV cable lines, for a cable modem. For local wired or wireless networks, a network adapter, also called a network card, a network interface card, or a NIC, inside your computer is part of this physical network. Every network adapter, including a network card, network port on a motherboard, onboard wireless, or wireless NIC, has a 48-bit, 6-byte number hard-coded on the card by its manufacturer that is unique for that device. See Figure 15.3. The number is written in hex, and is called the MAC, Media Access Control, Address, Hardware Address, Physical Address, Adapter Address, or Ethernet Address. Part of the MAC address identifies the manufacturer that is responsible for making sure that no two network adapters have the same MAC address. MAC addresses are used to locate a computer on a local area network, LAN. A local area network, LAN, is a network bound by routers or other gateway devices. A router is a device that manages traffic between two or more networks and can help find the best path for traffic to get from one network to another. A gateway is any device or computer that network traffic can use to leave one network and go to a different network. Level 2, Operating System Level. Operating systems use IP addresses to find other computers on a network. An IP address is a 32-bit or 128-bit string that is assigned to a network connection when the connection is PHY or SD made. Whereas a MAC address is only used to find a computer on a local network, an IP address can be used to find a computer anywhere on the Internet, see Figure 15.4, or on an Internet. An Internet is any private network that uses TCP/IP protocols. A large enterprise might support an Internet that is made up of several local networks. When several local networks are tied together in a subsystem of the larger Intranet, this group of small local networks is called a subnetwork or subnet. IP addresses are used to find computers on subnets, an intranet, or the Internet. Level 3, Application Level. Most applications used on the Internet or a local network are client-server applications. Client applications, such as Internet Explorer, Google Chrome, or Outlook, communicate with server applications such as a web server or email server. Each client and server application installed on a computer listens at a predetermined address that uniquely identifies the application on the computer. This address is a number and is called a port number, port, or port address. For example, you can address a web server by entering into a browser address box an IP address followed by a colon and then the port number. These values are known as a socket. For example, an email server waiting to send email to a client listens at port 25, and a web server listens at port 80. Suppose a computer with an IP address of 136.60.30.5 is running both an email server and a web server application. If a client computer sends a request to 136.60.30.5:25, the email server that is listening at that port responds. On the other hand, if a request is sent to 136.60.30.5:80, the web server listening at port 80 responds. Shows how communication moves from a browser to the OS to the hardware on one computer and onto the hardware, OS, and web server on a remote computer. As you connect a computer to a network, keep in mind that the connection must work at all three levels. And when things don't work right, it helps to understand that you must solve the problem at one or more levels. In other words, the problem might be with the physical equipment, with the OS, or with the application. How IP addresses get assigned. A MAC address is embedded on the network adapter at the factory, but IP addresses are assigned manually or by software. In Chapter 7, you learn that an IP address can be a dynamic IP address. IP address is assigned by a server each time it connects to the network. For dynamic IP addresses, a DHCP, Dynamic Host Configuration Protocol, server gives an IP address to a computer when it first attempts to initiate a connection to the network and requests an IP address. A computer or other device, such as a network printer, that requests an address from a DHCP server is called a DHCP client. It is said that the client is leasing an IP address. How to configure a Windows computer to use dynamic or static IP addressing is covered later in the chapter. An IP address has 32 bits or 128 bits. When the Internet and TCP/IP were first invented, it seemed that 32 bits were more than enough to satisfy any needs we might have for IP addresses because this standard, called Internet Protocol version 4, IP4, created about 4 billion potential IP addresses. Today we need many more than 4 billion IP addresses over the world. Partly because of a shortage of 32-bit IP addresses, Internet Protocol version 6, IP6, which uses an IP address with 128 bits, was developed. Currently, the Internet uses a mix of 32-bit and 128-bit IP addresses. The Internet Assigned Numbers Authority, IANA at IANA.org, is responsible for keeping track of assigned IP addresses and has already released all its available 32-bit IP addresses. IP addresses leased from IANA today are all 128-bit addresses. Next, let's see how IP4 IP addresses are used, and then you'll learn about IP6 addresses. How IPv4 IP addresses are used. A 32-bit IP address is organized into 4 groups of 8 bits each, which are presented as 4 decimal numbers separated by periods, such as 72.56.105.12. The largest possible 8-bit number is 11,111,111, which is equal to 255 in decimal, so the largest possible IP address in decimal is 255.255.255.255, which in binary is 111111111.1111111.1111111.1111111. Each of the 4 numbers separated by periods is called an octet, for 8 bits, and can be any number from 0 to 255, making a total of about 4.3 billion IP addresses, 256, 256, 256, 256. Some IP addresses are reserved, so these numbers are approximations. The FIRST part of an IP address identifies the network, and the last part identifies the host. When data is routed over the Internet, the network portion of the IP address is used to locate the right network. After the data arrives at the local network, the host portion of the IP address is used to identify the one computer on the network that is to receive the data. Finally, the IP address of the host must be used to identify its MAC address so the data can travel on the host's LAN to that host. The next section explains this in detail. Classes of IP addresses. IP4 IP addresses are divided into 3 classes, Class A, Class B, and Class C. IP addresses belong in each class according to the scheme outlined in Table 15.1. When IP4 addresses were available from IANA, a company would lease a Class A, Class B, or Class C license from IANA, and from this license could generate multiple IP addresses. Recall that the FIRST part of an IP address identifies the network, and the last part identifies the host. Figure 15.7 shows how each class of IP addresses is divided into the network and host portions. Looking back at Table 15.1, you can see that a Class A license is for a single octet, which is the network portion of the IP addresses in that license. The remaining octets can be used for host addresses or to identify subnetworks in the larger network. For example, if a company is assigned 87 as its Class A license, then 87 is the network address and is used as the FIRST octet for every host using this license, 87.0.0.1, 87.0.0.2, 87.0.0.3, and so forth. In practice, such a large network is divided into subnets. Because 3 octets can be used for Class A host addresses, one Class A license can have approximately 254 host addresses, or about 16 million IP addresses. Only very large corporations with heavy communication needs were able to obtain a Class A license. A Class B license leases the FIRST2 octets, and these FIRST2 octets are used for the network portion, and the last 2 can be used for the host address or for subnetting the network. An example of a Class B license is 150.35, and examples of IP addresses in this network are 150.35.0.1, 150.35.0.2, and 150.35.0.3. How many host addresses are there in one Class B license? The number of possible values for 2 octets is about 256 to 254, or about 65,000 host addresses in a single Class B license. A Class C license assigns 3 octets as the network address. With only 1 octet used for the host addresses, there can be only 254 host addresses on a Class C network or its subnetworks. For example, if a company is assigned a Class C license for its network with a network address of 200.80.15, some IP addresses on the network would be 200.80.15.1, 200.80.15.2, and 200.80.15.3. Class D and Class C IP addresses are not available for general use. Class D addresses begin with octets 224 through 239 and are used for multicasting, in which one host sends messages to multiple hosts, such as when the host transmits a video conference over the Internet. Class C addresses begin with 240 through 254 and are reserved for research. In addition to classes of IP addresses, a few IP addresses were reserved for special use by TCP/IP and should not be assigned to a device on a network. Table 15.2 lists these reserved IP addresses. Subnets using IPv4. Looking back at Table 15.1, you can see that a single class license network might have millions of hosts. Managing a network with so many hosts is not practical unless you divide the network into subnets. To divide a network into subnets, you designate part of the host portion of the IP address as a subnet. For example, suppose you have a Class A license of 69. Without using subnets, you have one network. The FIRST octet of all the IP addresses in this network is 69. The last 3 octets are used for host addresses, and the number of hosts in this one network is about 16 million. Suppose you divide this one network into 256 subnets by using the second octet for the subnet address. The subnets are 69.0.x.y through 69.255.x.y. The last 2 octets are used for host addresses in each subnet with a potential of about 65,000 hosts in each subnet, 256 by 254. The subnet mask used with the POR identifies which part of an IP address is the network portion and which part is the host portion. Using a subnet mask, a computer or other device can know if an IP address of another computer is on its network or another network. A subnet mask is a string of ones followed by a string of zeros. The ones in a subnet mask say, on our network. This part of an IP address is the network part, and the group of zeros says, on our network. This part of an IP address is the host part. If you don't divide a network into subnets, the default subnet mask is used, which is called a classful subnet mask because the network portion of the IP address aligns with the class license. For example, Table 15.3 shows the default subnet masks used for 3 IP addresses. In the table, the green numbers identify the network and the red numbers identify the host. These 3 subnet masks would be displayed in a TCP/IP configuration window like this. Subnet mask of 111.111.000000.00000.0000000 is displayed as 255.0.0.0. Subnet mask of 111.111.111.111.0000000.0000000 is displayed as 255.255.0.0. Subnet mask of 111.111.111.111.111.111.0000000 is displayed as 255.255.255.0. A network is divided into subnets when the subnet mask takes some of the host portion of the IP address for the network ID. This classless subnet mask does not align the network ID with the network octets assigned by the class license. Using our earlier example, The classless subnet mask for a Class A license of 69 that uses 2 octets for the network ID rather than the 1 octet assigned by the class license would be 11,111,111.00000.0000000 or 255.255.0.0. A classless subnet mask could also have a mix of zeros and ones in 1 octet such as 111.111.111.111.111.0000000, which can be written as 255.255.240.0. These classless subnet masks are used to subnet large corporate networks, public, private, and automatic private IP addresses. When a company applied for a Class A, B, or C license, it was assigned a group of IP addresses that are different from all other IP addresses and are available for use on the Internet. The IP addresses available to the Internet are called public IP addresses. A company conserves its public IP addresses by using private IP addresses that are not allowed on the Internet. Within the company network, computers communicate with one another using these private IP addresses. A computer using a private IP address on a private network can still access the Internet if a router or other device that stands between the network and the Internet is using NAT, Network Address Translation. NAT is a TCP/IP protocol that substitutes the public IP address of the router for the private IP address of the other computer when these computers need to communicate on the Internet. Because of NAT, a small company can rely solely on private IP addresses for its internal network and use only the one public IP address assigned to it by its ISP for Internet communication. IEEE recommends that the following IP addresses be used for private networks: 10.0.0.0 through 10.255.255.255 172.16.0.0 through 172.31.255.255 192.168.0.0 through 192.168.255.255. If a computer Fire ST connects to the network and is unable to lease an IP address from the DHCP server, it uses an automatic private IP address, a PIPA, in the address range 169.254.x.y. How IPv6 IP addresses are used using the IPv6 standards. More has changed than just the number of bits in an IP address. To improve routing capabilities and speed of communication, IPv6 changed the way IP addresses are used to find computers on the Internet. Let's begin our discussion of IPv6 by looking at how IPv6 IP addresses are written and displayed. An IPv6 address has 128 bits that are written as 8 blocks of hexadecimal numbers separated by colons, like this: 2001:000:000:000D3:9C5A:000CC. Each block is 16 bits. For example, the FireST block in the address above is 2001 in hex, which can be written as 0010, 0000, 0000, 0001 in binary. Leading zeros in a 4-character hex block can be eliminated. For example, the IP address above can be written as 2001:000:000:D3:9C5ACC. If blocks contain all zeros, they can be written as double colons. The IP address above can be written two ways: 2001:B80:000:D3:9C5ACC, 2001:B80:D3:9C5ACC. To avoid confusion, only one set of double colons is used in an IP address.
In this example, the preferred method is the second one, 2001:00:B80:D3:9C5ACC, because the address is written with the fewest zeros. The way computers communicate using IP6 has changed the terminology used to describe TCP/IP communication. Here are a few terms used in the IP6 standards. A link, sometimes called the local link, is a local area network, LAN, or wide area network, WAN, bounded by routers. An interface is a node's attachment to a link. The attachment can be a logical attachment or a physical attachment using a network adapter or wireless connection. For example, a logical attachment can be used for tunneling. Tunnels are used by IP6 to transport IP6 packets over an IP4 network. The last 64 bits or 4 blocks of an IP address identify the interface and are called the interface ID or interface identifier. These 64 bits uniquely identify an interface on the local link. Neighbors are 2 or more nodes on the same link. 3 tunneling protocols have been developed for IP6 packets to travel over an IP4 network. ISATAP, pronounced ISATAP, stands for Intrasite Automatic Tunnel Addressing Protocol. Teredo, pronounced Teredo, is named after the teredo worm that bores holes in wood. IP6 addresses intended to be used by this protocol always begin with the same notes. 32-bit prefix, called FIS bits. Teredo IP addresses begin with 2001, and the prefix is written as 2001:32. 6-4 is an older tunneling protocol being replaced by the more powerful Teredo or ISATAP protocols. IP6 classifies IP addresses differently from that of IP4. IP6 supports these 3 types of IP addresses. Using a unicast address, packets are delivered to a single node on a network. Using a multicast address, packets are delivered to all nodes on a network. An unicast address is used by routers. The address identifies multiple destinations, and packets are delivered to the closest destination. A unicast address identifies a single interface on a network. The 3 types of unicast addresses are global, link local, and unique local addresses, which are graphically shown in. Here is a description of each of the 3 types. A global unicast address, also called a global address, can be routed on the Internet. These addresses are similar to IP4 public IP addresses. Most global addresses begin with the prefix 2000:3, although other prefixes are being released. The /3 indicates that the FIRST3 bits are FISed and are always 001. A link local unicast address, also called a link local address or local address, can be used for communicating with nodes in the same link. These addresses are similar to IP4 private IP addresses and are sometimes called link local addresses or local addresses, and most begin with FE80:64. This prefix notation means the address begins with FE80 followed by enough zeros to make 64 bits. Link local addresses are not allowed on the Internet. A unique local unicast address, also called a unique local address, ULA, is used to identify a specific site within a large organization. For example, an organization might have these 2 sites, employee.mycompany.com and support.mycompany.com. The address prefixes used for unique local addresses are FC00:7 and FD00:8. The global ID portion of the address is assigned by the organization. Unique local addresses are not allowed on the Internet. They are hybrid addresses between a global unicast address that works on the Internet and a link local address that works in only one link. Notice in Figure 1510 that global and unique local addresses contain a block labeled the subnet ID, which is the last block in the 64-bit prefix of an IP address. Recall that when using IP4, the subnet could be identified by any number of bits at the beginning of the IP address. Using IP6, a subnet is identified using some or all of the 16 bits in the subnet ID block. Using IP6, a subnet is, therefore,
Identified is one or more links that have the same 64 bits in the IP address prefix. This definition implies that a local link is itself a subnet. Table 15.4 lists the currently used address prefixes for these types of IP addresses. In the future, we can expect more prefixes to be assigned as they are needed. That will be all for this video, so be sure to hit that like button and subscribe to CTech and enable that bell icon so you don't miss any further videos with us.